Let me share the slides. Welcome to this course on computer vision. This course, we would like to have it as a self-contained course on image processing and computer vision. So I assume no background on either image processing or on machine learning for understanding the computer vision or performing the computer vision task. So formally, we will try to bring in what is computer vision. So what are the basic concepts or basic background that is required to understand computer vision. And then we will also see some of the evolutions in computer vision. So we give more importance in this course to the conventional methods of computer vision. Of course, I have seen some of the students already have taken either machine learning or taking deep learning. So those, of course, will be helpful in your mini projects. But for the understanding of basic conventional methods of computer vision, so I would consider that all are equally placed. So those who have a little bit of mathematical background and have interest to programming or has a little bit of skills in programming is good enough to understand this course. However, there will be a set of both written and programming assignments as we go along in the course. And there are some concepts which need a little bit of mathematical understanding. Also, some concepts of other domains. Say if we bring in a kind of transform-based domains and so on, for some topics to understand them better. This is the as you know, this is a 3-credit course, and we will have it on the as per the slots. Vaishnavi and Sumant will be TS for this course, and you can contact them either any of us. So either TS or me through mail or phone. So what essentially is the objective of this course? As I mentioned, we would like to understand from the basics what is computer vision. So you might have, and so I listen when some of you are discussing on computer vision. It's not a topic of computer science as such. Of course, computer science, one of the topics of computer science is also computer vision. This is a sub area of artificial intelligence. If we consider very broadly the definition of artificial intelligence in a broader sense. But it's also has been driven widely from the signal processing and image processing backgrounds. So it's a blend of, I would say, in image signal processing aspects and a kind of artificial intelligence aspects together. So we will see as we go along what are the essential elements to understand computer vision better. Of course, it is vast subject or vast area. So we will not be exploring on all the topics of computer vision. So computer vision can be seen in different perspectives, either from the way the image gets formed to the way that we interpret the image, and then the way that the image coordinates and the physical coordinates relate. So it's different perspectives of computer vision are there, and then even if you see the courses on computer vision, they vary a lot. In sense, some of them nowadays because of deep learning applications or deep learning intuition into the computer vision. So some of the courses on computer vision focus more on deep learning as well, because that gives reasonably state-of-the-art results now. And some of the courses on computer vision, those who are well known or widely referred, they are mostly on very conventional computer vision as well. And some of them is a blend of both conventional computer vision and deep learning or machine learning. So we will, and some of them go from the geometrical perspective of computer vision and so on. So we will see what is the scope of the computer vision course that we discuss. So broadly, computer vision is defined as the ability or the ability that we can impart to a computer to infer from images. So the ability of vision that we have, can we impart the similar abilities of vision to the computer through the computer algorithms or computer processing? This is also encompasses inferring from images that a camera takes, or a video from a video, and so on. So this is the broad definition of computer vision. But however, as I mentioned, the computer vision also has different flavors of it. So we will see what flavors we would consider and so on. So we will try to understand what is low level vision, say even in the human vision. So they divide the vision into low level, mid level, and the high level vision processing. Say low level is mainly on the on the processing task. Say for example, if I give an image, so can I process it and get an output of an image that either suits my job. Either let it be visually pleasing, or let it be free from noise, or let it be enhanced of contrast, or let it has better details of the image, or whatever. So it's roughly considered as the low level vision. And the mid-level vision is broadly on, can I get a little bit of inference? I may not specifically get the whole inference of the image, but can I get the, different regions of the image separated? They may or may not be labeled as well. So that's kind of things are mid-level vision, and then high-level vision is to make an inference from the image. So we will see actually as we go along, how does the image formation happens, and then what the difficulty of inferring from images. As we are saying, we are seamlessly performing the ability to infer from images. But what's the difficulty? Why do we need to study it as a subject of computer vision? So that we bother about, or we see about in the subsequent discussions. And we will also see what, if you want to infer from images, where to see. For example, say for humans, so we don't have these questions because we do it almost by default or without knowing how we do. So we assume that it's a default task. It's a intuitive task for us to look what we want to look and where we want to look is an intuitive task based on the objective we have. But for the image processing or for computer vision, it's not not that so simple. So we will see that. So why it's not so simple, or how does the methods have evolved to perform this? So in fact, it has a half a century progress, and then now given almost a century progress in terms of evolving the computer vision methods. Of course, the recent era has put this with the blend of deep learning, it has put into the application level much more rigorously. But the conventional methods has an elegance of how the modeling has to be done if you want to infer few things. So that kind of intuition and modeling perspectives which will be much more evident and will be clear only when we understand the conventional methods. Once we understand them, can we perform even with a kind of a learning setting or in an automated setting, etc., is the answer that is usually given by deep learning algorithms. So I would consider that it's a complementary. The course is complementary to the course on deep learning. It's not a substitution to the course on deep learning. And either both ways. So this course is also not a substitution for deep learning. The deep learning is not substitution for this. We also see there are several challenges in inferring. As I mentioned, we will see how the methods have addressed these inferences and how the field has progressed. We also see the role of learning. As I mentioned, nowadays the learning methods has come up as a breakthrough almost in computer vision. What is that? What the contribution they can do? We see that to a very minimal details in this course, because in next semester there will be courses on machine learning for image processing or deep learning and so on. So those who are introduced to this field now, or who are starting on the image processing, computer vision, machine learning area, I would say that I would like to put this as a context of inference from images, understanding the image, and then understanding the difficulties of the how we do infer from images. That's the context of this course. And the next course, probably either on machine learning or deep learning, they will bother about bringing, or they will discuss more about bringing the learning aspects for these same problems and solutions. So we'll see a couple of conventional solutions now, and we see very briefly on the learning based solution as well, but that's a brief for discussion on learning. And then we subsequently see what are the, say, when we want to infer from images, there are three major things that people look for. And one of the major thing is to get the 3D inference from the images, because images are nothing but the 2D projections of the 3D scene. So if we are only left with the 2D projections, so can we get back the 3D reconstructions of the scene? That's a very important area, or a vast area again. So we will be sampling from these different solutions and the problems of computer vision. And we also will be discussing a little bit of sampling again on the learning front. So we assume that once you complete this course properly, you will be familiar with the basic concepts of image processing and computer vision. You will have a solid understanding of the background that is needed for both the image processing and computer vision. And you will also appreciate the current exploding applications of computer vision in all fields. So name a field, there is an application of image processing and computer vision nowadays. So you will also get to know a little bit of programming, or you have to vet yourself with the programming, probably in Python, mostly in Python. And then you need to code basic algorithms and concepts to visualize the processing and algorithms that they do. Because as you know, this is a image processing, so we understand much more in images and more in say computer vision, inferring and so on from images. We also will understand the difficulty of a computer. Okay, when we start coding it, so in the computer, on how it understands, how it visualizes, how it interprets, and so on. Even for our understanding of visualization of what these computer vision methods does, these kind of programming assignments are must. There will be some background mathematical details that are discussed along with the methods. Whenever it's required, even some of the learning methods are also discussed with some of the methods. So let's understand how a camera forms an image. So we know that for a visual perception, we have a we see an image, and there is a retina, and that takes the image, and then there is a visual cortex behind, and the image gets formed in the visual cortex, and from that we infer the scene information. And we have two eyes, so through two retinas, the projections of the scene goes, and there is, since the two eyes are displaced, there will be slight difference in the projections that we get in the visual cortex. And from that we try to infer all the aspects, what is there in the scene, what is the distance of different objects, what are the objects, and many other things. So as for the camera is concerned, or camera for a camera, so camera itself is a mathematical model, and it has a sensor elements. So what each sensor element does in a camera is to look at a small region in space. This is essentially, say if you consider this is the lens of a camera. Okay, so it looks at a small region in space. Okay, in that region, it tries to bring in the average intensities of that region. Okay, and then try to put it at some location. Okay, in the image plane. So the image plane is in 2 dimensions. As you can see here, image plane is a 2-dimensional representation of the 3-dimensional image, 3-dimensional object. So when we do that, what happens? So each of the point here, essentially the camera can be modeled in 2 ways. One is with lens and other is without lens. When we model with lens, we assume that the lens gather the information in a better way, and then they assimilate the information and then put it at the image plane. Whereas the other simple model of the image formation is with a pinhole camera. So the idea here is if we just see with a small pinhole, so then the information of the object comes there and gets projected on the image plane at different locations. So what happens here? Because each point gets traversed through this pinhole, we get an inverted image of the scene. So, but for visualization purpose, we assume there is a virtual image plane, and then there we get the straight image. This is the virtual plane we consider. But however, the image formation happens in a inverted manner. But however, you can relate the height of the object, okay, the some of the coordinates, x and y coordinates of the object effectively through triangulation and so on. So we will bother about the mathematical models or mathematical details of exactly how the 3D representation goes to 2D later. But this is just an idea of how the image formation happens in a pinhole camera first, and then this is in a lens-based camera. So as I mentioned, so there is a 2D representation of a 3D scene. So as you can see here, this is a pencil like this. So you can see here, you are looking a pencil as a straight pencil when you see an image there. But there is I have put this pencil in 3 dimension, okay, with an inclination. So the height variation there is not seen in 2D representation. But however, if you see here the projection of it, so what's happening here? This is a pencil that is seen in a 3D, and through pinhole camera again we are capturing here, and you can see here this is an inverted image. But however, you see that this is in 3D plane. So what happens? So in X and Y plane, so how much, say, what is the location of this pen or pencil will get coded here, encoded here. So you can note that the X projection is this much, and then say for this, for example, and Y projection is this much, or X projection is this much and Y projection is this much. Based on how we denote X and Y planes, we can encode the information of the X and Y projections of this object. However, the Z information may not be directly available. That is why we need a little bit of processing and understanding to get the 3D art depth information. Even to get the 2D information, it is not so straightforward to say that this pencil has these many displaced, or these many centimeters displaced in X plane and these many centimeters displaced in Y plane. It's not so straightforward, because what the image captured will be in pixel space. Pixel meaning picture elements. So what usually happens is there is a CCD sensors or CMOS sensors. So we have, say for example, if we say 1 megapixel camera, then there will be 1000 cross 1000 CCD array elements or CMOS array elements, sensor elements. So you have 1000 cross 1000 sensor elements here. Each sensor element will be looking a small region in space. Okay, so it takes an average intensity of the space and puts it as a value here. Likewise, each of the sensor element will look at and put a value here. So finally, what we get is a 2D representation of a 3D space, and each sensor elements segregates the average intensity values and put it there. So just to get a better idea on what a image is for a computer, let's take an example. So hope you people are able to recognize the image that we are seeing here. So this is from our permanent campus. So one of the image you see as is the grayscale image. This is referred to as grayscale image, where you have only intensity variations from 0 to 255 or 0 to, based on the number of bits we represent each sensor element. So it can be either 0 to 255 or 0 to 1024 or whatever, 2, 3 and so on. Okay, so the this is the color image. where you have different channels to represent an image. So how does the computer see an image is more evidently is being displayed here. So you see that say if you see a small region, okay, and want to understand, okay, what is there in this. So for us, we see that there is a wall here and there are some probably window doors here, and then there is a some kind of window open or ventilation here and so on. So we see some kind of inference directly from here. But for an image, if you want to, for a computer, if you want to see and interpret what is this, okay, then it sees it as a matrix of elements. Okay, it sees more like a matrix of elements like this. Okay, so wherever there is a black region, okay, so the average intensity of the pixel element given by at that location is very the value of the pixel element or picture element or pixel is very intensity value is very low because it is dark region, and at that region you can see that the values here encoded are lower side of the 0 to 255. Whereas in a brighter side, say when we see that there is an object here, there is a high intensity here, we see that the intensities are on the higher side of the 0 to 255. Okay, so I think this representation has gone even up to 256 and so on. So maybe it's a slightly the number of bits to represent at each pixel element are higher than 8. So usually what happens, as I mentioned, so there is a sensor element that looks at a small region, each of the small regions here, and that sensor element takes an average intensity and puts a value as a matrix here. So as you can see, this is an average value of this is put as a average value of this is put as a value at this corner. Okay, so average value of this is put as a value here. Okay, so how much region in mm or centimeters a pixel looks at or a sensor element looks at depends upon the resolution of the camera. See, there are different resolutions when we speak about resolutions. So one is spatial resolution. Spatial resolution means how many sensor elements are there. So as I mentioned, 1 megapixel camera means say we can assume that 1000 cross 1000 sensor elements are there. Each sensor element look at a small region somewhere. Okay, in this space, corresponding region in this space. So that is referred to as 1000 cross 1000 pixels is referred to as spatial resolution. Of course, this is in the pixels, the spatial resolution is 1000 cross 1000, but the actual spatial resolution is each pixel, how much does it look at in the space. So for example, each pixel may look at say 1 mm cross 1 mm region in space, or it may look at 2 mm cross 2 mm, 5 mm cross 5 mm region, okay, in space. It depends upon what, how much region a pixel element looks at in space. Depends upon what? It depends upon the camera resolution that we usually call as camera resolution. So that is, say for example, 1 megapixel camera versus 4 megapixel camera. If we see a 4 megapixel camera looks at, so roughly 1/4 of the region that a 1 megapixel camera looks at by a single sensor element. Okay, because 1 megapixel camera takes a region of say 4 mm cross 4 mm as one value here in a sensor element as an intensity value here. Average intensity of 4 mm cross 4 mm if it takes as a single element, whereas the other one, the 4 megapixel camera looks at a 1 mm cross 1 mm region as one single pixel element value. Hope you understand that the spatial resolution. And intensity or photometric resolution is the other thing that we usually consider as an important thing to understand in image. Say if I have at each, say I have measured the average intensity values, but what range should I put that values in? Say, should I put those values in 0 to 255? Should I put these values in the range of 0 to 1024? See, if I'm able to put the values with 0 to 102 or 0 to 1023, it means that I'm using 10 bits. Okay, to represent a single pixel element value there. So each sensor element value at there, which it looks at the real scene, is represented in a 10-bit representation. So if I have 10 bits to represent, I can say, for example, I can discriminate the intensity variations much more evidently than an 8-bit representation of the intensities. So this is referred to as intensity or photometric resolution. Usually, if you see all our cameras, most of our cameras are with 0 to 255 intensity resolution or photometric resolution, where you can see we represent with an 8 bits. Each sensor elements represents its average intensity at that location by 8 bits. If you see synthetic aperture radar images or satellite images and so on, their intensity resolutions will be much higher. And the reason being, they want to discriminate much more when they want to image a large region. Okay, and then distinguish a small, very like over a lower spatial resolution. So what do we mean by lower spatial resolution for a satellite image? Lower spatial resolution means, say, pixel element. Now if we take a usual camera, each sensor element, it may look at, so you can see that actually a small region here, say it may look at 1 mm cross 1 mm and put a value here. Whereas the satellite image, if I take from the satellites or from the UAVs, usually what happens, they can't look 1 mm cross 1 mm and put a intensity value at a given sensor element. They usually look at 30 centimeters as a single pixel element and put it there, or 1 meter, whole 1 meter in region, they average and put a single intensity value there. So it because they look at much higher regions than the region that a conventional camera looks at. This is referred to as field of view. So field of view of a camera is also represented in two ways. One way is the area that it looks at. So how much area can it look at? That is the field of view. Other way is how much angle the camera can sense. So that's the other way of considering a field of view. So usually satellite images that the cameras in this synthetic aperture radar cameras or cameras that are used to capture the satellite images will look at much higher spatial region, field of view, than a conventional cameras. And there is other thing that is usually also considered for like understanding how well we capture a details of a scene, that is in terms of videos, that is referred to as temporary resolution. So if say if I want to perform a arc processing task, I can't take a conventional camera and process at 30 frames per second. Usual frame rate that we capture to our conventional cameras is 30 frames per second. So it's good enough to capture the variations that we, the movement of many objects in the natural scenarios. So because the motion of objects will be much lower than 30 frames per second, that means we won't move faster than 1/30th of a second. Whereas if you want to capture the variations of a arc, for example, then or a bullet firing experiments kind of things, you need to have a much more camera frames per second, frame rate that we call as. That is referred to as temporary resolution. So we probably conclude the discussion here and see in the next class on say how do we infer better, or what is the problems of computer vision in general. So we also see on the grading pattern and other things in the next class. So this is an RGB image. So as we see nowadays all RGB images. So where say there are 3 channels to capture the information of the image. One is red channel and blue channel and green channel. So you can see here by looking at it itself, you should be able to make out what red channel does, what green channel does, and what blue channel does. So you can see that the red channel, okay, will have higher intensities for the red regions. Okay, so whereas the green channel will have higher intensities for the green regions. Okay, and then similarly, blue channel will have higher intensities for the blue regions. Okay, so this is the basic understanding of images and then image formation. We will see more details of this and then analyzing the images and then inferring from images and the relation to the related fields and the concepts required in the subsequent classes. Thank you. If you have any quick question, you can ask.
Sir?
Yeah, please.
Sir, are you offering a laboratory course for computer vision this semester?
Yeah, no, No lab is as such planned, Mahesh, but we will be having a series of programming assignments, and our TAs are familiar, or they will make you familiar, okay, with the basic coding of Python and so on. Okay, so you can understand and learn quickly on those aspects, and probably we will provide some code snippets where you need to fill the gaps to perform particular specific tasks. So there will be some programs that are to be done at the say from scratch, and they are mostly to understand the concepts. There will be some programs that to understand the basic application of computer vision as well.
Okay,
So
sir.
through programming assignments, we will you are supposed to learn,
Okay,
and they
sir.
are part of the course.
Okay, sir.
Yeah. So hopefully after half a semester also, we will have a lab completely set up there. There, if you wish to sit in the lab and have a formal lab session 1 or 2, we can manage to have them.
Oh, okay, sir.
Any other questions or doubts?
Yes, sir. Hello.
Hi, Milan.
Yes. So I wanted to ask, can we code on some other platform like MATLAB or Python?
Yeah. So I probably it's okay to code even in MATLAB, not a problem. But if you would like to learn and more apply on this, so then Python is welcome, because Python also looks almost similar to MATLAB. There is not too difficult to learn it, but we don't mind. So if you for some reasons and based on your other background, you would like to consider MATLAB in itself to code, you can code it. Only thing is, whenever we are asked to code from scratch, you have to code from scratch only. You should not use the inbuilt functions.
Okay. Thank you.
Yeah. Thank you. Any other questions or doubts to discuss? Thank you then.
Hello, sir.
Hi.
Sir, will the this PDF will be shared to our classroom?
Yes. Yeah, I will upload this in Google Classroom.
Thank you, sir.
Yes. So I would suggest all of you to register in Google Classroom if you have not done. There we will communicate on the probably even share the video lectures as well as we whenever we have in online session. So mostly after 2 weeks we will resume. We assume. Thank you then.
Excuse me.
Yeah, tell
Sir, I have a doubt regarding spatial resolution.
Yeah,
So it is the area that a sensor in a pixel looks at.
right, correct. And usually, say if we ask in terms of a camera spatial resolution, we say that the number of pixels it gives. So 1 megapixel camera, 4 megapixel camera, this is also referred to as spatial resolution, kind of resolution of camera we call pixel resolution. If you want to separate from spatial resolution to pixel resolution, I would encourage, and pixel resolution is the 1 megapixel and 4 megapixel. Spatial resolution is a pixel, how much it looks at in the real scene.
Yes, got it, sir.
Yes. Any other doubts or questions? Thank you then. We'll meet again on Wednesday, coming Wednesday. Thank you.
Thank you, sir.
Thank you, sir.